Yeah, welcome to all the course participants in the third lecture under the series of Global Navigation Satellite System. So today we will cover the satellite-based augmentation systems, including the ISRO system of India, that is the GPS-aided GEO augmentation navigation, that is the GAGAN. So we will do a bit of revision what we have done. I just wanted to show you this book also. You can just Google it, and by giving your email ID, you can get access to download this book also. So this was just for your reference. So we'll discuss what are the various augmentation systems and why we require augmentation systems. Then we'll discuss the different type of augmentation systems and how we are able to improve the positional accuracies using the S-bus systems, which are dependent on the GNSS basically. And then we will touch upon the core sources and the aviation applications. So in the last two lectures, we have seen that using the GNSS satellites, we are primarily getting three parameters. That is the position, which in itself includes the latitude, longitude, height above the given datum. So we are primarily using the WJ74, and then we get the receiver velocity also, and then we get the time also. And all these things we get in a common reference frame. Then we see that the ICAO is also an important party in this whole GNSS framework. Then we have covered the 4 global navigation satellite systems, out of which the 3 are completed: Navistar GPS, GLONASS, and BEDO. They are providing their full services. However, Galileo is under completion. So it is also partly operational in parts of the world. Then we discuss the various signals: L1, L2 carrier waves, L5 carrier wave, CA code and the P code. We have discussed them. We discussed the 6 orbit based Navistar GPS system, and then the 3 orbit based system of GLONASS and Galileo, whereas BEDO uses about 7 orbits. Then we also discussed in the yesterday's lecture what are the different type of receivers: single frequency receivers, dual frequency receivers, multi-frequency receivers, what type of accuracies they are giving. Another way to classify the GPS receivers, that is the geodetic mapping and navigation receivers, that also we did yesterday. Different type of sources of errors that we have seen yesterday. And this will again be covered in the last lecture on the processing in detail. Then we have covered the different type of processing schemes for the static, rapid static, stop and go, kinematic, and then the differential GPS, in which we have understood that we need 2 GNSS receivers. One we place at the known location, and that known location we call as the base station, and the place where we install the GPS to compute the new location or the unknown location in the field, particularly for the GCPs and the checkpoints are required for the various applications, including the georeferencing of the datasets or the triangulation of the stereo datasets. And this also we have seen that either we can do the processing of the GPS data, DGPS data, either in the post-processing mode or in the real-time kinematic mode. So today we will cover the satellite-based augmentation system, and primarily, as I was telling, the ICAO, that is the International Civil Aviation Organization, who has the responsibility to develop the standards and procedures to support safe transmission of the communication, navigation, surveillance, and air traffic management system for all the aircrafts globally. So they basically have the responsibility for that. So they are laying down various terms in this line. So in this case, what is happening that GNSS as a standalone facility is not able to provide us the required accuracy for the purpose of aviation or for the some critical applications where real-time kinematic accuracies are required with higher accuracy. So there we are making the satellite-based augmentation systems, SBAS systems, which are providing us a accuracy which is over and above the accuracy of the GNSS. So GNSS standalone accuracy is 10 to 20 meters, as we have understood. If we are doing the DGPS survey, then also with the best of our methods, what we do, we are getting the 20 centimeter or so accuracy. This 20 centimeter accuracy of GNSS is with respect to the satellite laser ranging systems. That is the way to qualify it actually. Now our requirement is a higher accuracy in the real time mode. So for that purpose, we are using the DGPS method itself actually, but in a planned way actually. So SBUS is providing wide area or regional augmentation through the use of additional satellite broadcast messages. So primarily what happens that we have multiple ground stations on the ground, on the earth, which have known locations. So they are already accurately surveyed. So they act as the base station. What we have understood in the DGPS, so these all stations basically act as the base stations and they generate the correction parameters for the operations nearing to those specific stations. Okay, so nearer to the station, we are higher accuracy we are going to get. And in this, geostationary satellites are also playing important role because these correction messages are sent to the geostationary orbit satellites and they broadcast the correction parameters to the user again. And all this is happening in the real time. The SBUS is also called as the wide area DGPS system. Okay, so at the core of it, the processing which is required for differential GPS is only existing in the SBUS also. But it's a very planned fashion, the way we make the reference station on the Earth at various locations. So various countries are involved into this work and they have laid down different reference stations. So through the broadcast ephemeris data, which is coming from the GNSS satellites, as shown here from the GPS, they get the broadcast ephemeris data and they compute the errors at the reference station. Why they are able to compute it and how they are able to compute it? They are able to compute it because the correct location is already known. So that epsilon x, that is x minus x dash, epsilon y, epsilon z, that is the deviations in the xyz through the broadcast ephemeris can be computed in real time. And this correction parameters are then uploaded using the uplink station to the geostationary satellite. And the geostationary satellite further broadcasts the corrected parameters to the user. Now geostationary satellites, like 3 satellites can cover the entire Earth very easily, right? So they have a very large footprint. However, we should understand that when we are talking about a user, the nearer the user will be there from the reference stations, the more accurate value user is going to have. So now there are different SBUS systems, like for the US region, it is called the WAS, which is the Wide Area Augmentation System. For India, it is GAGAN, GPS-aided GEO Augmented Navigation System. For the European region, it is the European Geostationary Navigation Overlay System. And similarly, AMSAS is there for Japan, Multifunctional Satellite Augmentation System. Then the Regional Navigation System QZSS is also there for Japan. Then SDCM is for the Russia. SNAS is for China. And for Caribbean countries, it is SACCSA. So this one is the one which is used for a good number of countries. Now, when so many systems are there, as we discussed earlier also, we have systems in the space segment, which consists of so many satellites belonging to different nations and different constellations, like the GLONASS of Russia, Navista GPS of US, BEDO of China, and Galileo of European Union, IIRS of India, and the QZSS of Japan. So all these are working together with the system. Some of the regions, particularly the L5 frequency, and at places L1 frequency, which is common to many of these systems, is used for the cross or for the interworking of the different systems together. So even if we have 4 signals from 4 different systems, we are able to process it. Why? Because we are working on it as a global navigation satellite system. So now when multiple systems are there, it is to be checked that mathematically are they functioning properly. So that thing we are considering as the integrity. So integrity means what kind of trust we can have in this information which is coming from the GNSS or the SBAS system. So that has to be seen and maintained actually. So then we will further cover the NDGPS codes and GDGPS later on along with the IGS stations. So this is the kind of setup where the satellites in the geostationary orbit, like this VASP, PRN 135, 138, 133. In case of GAGAN, it is 127, 128 for GSAT 8, 10, and GSAT 15 is also operational. So these geostationary satellites play an important role to disseminate the correction parameters to the user in the real time. So this is the dense availability of the reference networks across various parts of the globe. So many of the systems are functional, some are planned, and some of the systems are already under expansion. So basically what is happening that we are able to get good signals providing us an availability of vertical accuracy of the order of 35 meters and horizontal that of 40 meters for almost all part of the globe. Leaving the polar region, for most of the area we can get that. So that is shown here in this figure. Now in this basically, as we can see here, the ground-based stations have also been playing important role actually, from the very high frequency VHR omnidirectional range. See, when GNSS was not there, they have to be connected either through the ground stations or through the ATC, that is the air traffic control management system that they have to be in touch with, or the distance measuring equipments are there, or the other systems which have been there since World War II, like the GE system, SON system, console, or the tower-based terrestrial systems like the Omega, Chaika, and Lawrence, which we covered in the first lecture. So these systems have also been in the list of sensors which have been guiding the aircrafts during the travel. Because aircraft based management system also required that the receiver autonomous integrity should be maintained. What does that mean? That means that the assessment of the signals is done, that whether they are fulfilling the requirements for the area navigation, that is the RNAV. So we will see the specifications of RNAV also. Now, as per 2021 latest list has also come, there is a large number of stations which are non-ILS. That means they do not have the integrated landing services or the systems at the airport. So around 1200 airports are there in US who are fully functioning correctly on the basis of the vast wide area augmentation system, VAS. So that much dependency they have. So almost about 4,000 airports which are having the VAS localizer systems for performing, about 1200 of them are on the non-ILS airports. That means they are taking off, landing, or the ATC control. All of those things are going through the GNSS. Their landing and taking off operations are fully controlled by the GNSS based SBAS systems. That is the VAS in case of the US. Then there are very high frequency systems also based on the ground. So it is possible that from the ground itself, we can send the correction signals to the aircrafts based on the ground-based augmentation systems, which are also called the local area augmentation systems. So ICO has a manual which is called the performance-based navigation manual. So as we can see here, they have a different requirements: RNAV1, RNAV2, RNAV4 during the departure of the flight, then when it is traveling over the land and the ocean, and when they are arriving at the airport. So when they are in the approach region of the airport, what type of accuracies they require. So this area navigation 10, area navigation 5, 2, 1, 4. So these different type of area navigation schemes have been developed which define what type of accuracies are required. So we can see here that finally when we are approaching, an accuracy of 0.3 nautical miles should be there in the with the aircraft actually. So this is a very high accuracy when we are approaching the airports, and we have standard instrument departure routes and standard arrival routes on which this all accuracies will be required. So the SBAS systems are able to provide much better accuracies. If we talk about the war systems, then they can provide an accuracy of 75 nautical miles using the Doppler VORs at a or as a 60 nautical miles otherwise. So this is the again how we are being benefit from the VAS system. So we have a takeoff of the aircraft, and another advantage what we have is that since if we are using the SBAS based systems, we need not to be connected with the DME or the VOR systems on the ground, and that enables us to fly point-to-point flight also. Otherwise, we have to be connected with the DMEs or the VORs, and because of that, we have to follow the zigzag path. Okay, that you might have noticed. Otherwise, when we are using the SBAS systems, then we can fly point-to-point. So you can see from one airport to the other airport directly in a single line we can travel. In a single line means single line on the earth. That is the footprint of the travel path. So what will be the resulting thing which happens because of that? Resulting thing is that the shortest path we are using. So that will increase the flight efficiencies. It will save fuel also. So it is environmentally beneficial. The schedules can be better packaged, and they will be more predictable with the increased safety and increased capacity in the airspace. Because if we have more accurate values of the location of the aircrafts, we can pick or we can allow more number of aircrafts to fly safely in a given region, and it will definitely reduce the delays also. So based on the area navigation or RNAV1 accuracy statement, see what we are getting from the GPS is of the order of 36 meter accuracy horizontally and vertical accuracy of the order of 77 meters. But when we are performing the VAS based operations, it is possible to attain an accuracy of 16 meters in horizontal or 4 meter in vertical, and further it can be improved with the verification of values for the horizontal and vertical measurements. So thus the satellite based augmentation systems are helping the aircraft industry very largely, and it is good if all the systems are being fitted with these systems. So again, as I have told earlier, so VAS, which is maintained by the Federal Aviation Administration and the Department of Transportation, how it is happening that there are master stations on the ground where we have the known locations of different reference stations. All the data sets are being collected at the master station, and it is being uploaded with the correction parameters through the uplink station. And this uplink station sends the correction signals normally in the C-band to the geostationary satellites, which are mainly the communication satellites, who in turn disseminate the corrected signals to the user. Now these corrected signals, it's not that they are available only for the aircraft industry. All the GNSS receivers which are SBAS enabled and being in use for any of the applications where GNSS is used, they all will be able to receive this as passing. So there is no breakage of signals for them, and it's not that their service is only for the aircraft industry. It is available to the other users also. So this vast system, in all this, it is able to do the corrections for the ionospheric errors, timing, and for the satellite orbital errors. So all these corrections are done along with the integrity check. So integrity, as I told, it is the most important thing. So integrity is maintained completely between the systems which are part of the entire SPAS, whether they are on the ground as a reference station or the master station, or whether it is the geostationary satellite which is disseminating the correction parameters to the user, or even if it is the GBAS or the last system, wherein the direct signals are being sent to the user through the VHF antennas which are there on the airport. So these are VAS is also providing all the benefits which we have discussed earlier. So in case of the LAS or GBAS system, the VHF antenna is used and it directly transmits the correction parameters to the aircraft. So again here also the aircrafts directly get the highly accurate coordinates while landing or takeoff. Okay, en route when the aircrafts are there, at that time the accuracies deteriorate a bit, as I already told, because of various reasons, as we discussed in the previous lecture also, because if they are near to it, the correction parameters will remain same. If they are far from it, then what will happen? The weather conditions may be different, and then the ionospheric correction or other correction parameters which have been sent to the aircraft or the user may not be that accurate, which it is for the neighborhood region of the reference stations. So similar to VAS, GPS aided geo augmentation navigation system, that is the GAGAN, has been developed in India in collaboration with Airport Authority of India by ISRO. And here Raytheon has established various reference stations across the globe, and the signals are approved for the en route operations, that is RNP.1 on December 30th, 2013, and subsequently they are approved for the precision approach services on April 21st, 2015. So all these signals are available for the user. GAGAN was the first SBAS system to serve the equatorial region also. So GAGAN is fully functional, and it is suggested that this should be available now for all the aircrafts besides the other users who want to take advantage of it and take the benefits of the GAGAN service in India. Here, although we have to understand that GAGAN is a dependent system. So GAGAN, basically the primary input for GAGAN comes from the Navistar GPS. So our reference station locations around India are known using the previous survey. So all these locations are already computed, and based on that, ionospheric correction parameters are also generated for the Indian region, and that further enables the correction in the Indian region. So the nearer we are to the reference stations, the better parameters we are going to get from the GAGAN system. So as I was showing, so these are the various stations established in India, and we also do have a system of GBAS and LAS system on the ground where VHF antenna can send the signals to the aircraft. Currently about 15 stations are operational, and we have plans to increase this number up to 45. So in the times to come, we will have about 45 stations across India where the GAGAN services will be directly available through the antenna-based systems as well as through the GAGAN. But as I told you again, as we are near to the reference stations, more accuracy will be there. 3 systems we launched in the geostationary orbit for it, that is the GSAT 8 and 10, which are giving service from beginning, and the GSAT 15 was kept as a spare, and now that is also operational. So GSAT 8, GSAT 10 and GSAT 15, they are providing us the various services for the GAGAN to provide us the correction signals. So in this case, in the case of GAGAN also, we have all the advantages. We can have point-to-point flying. We can have more compact airspace which can be done. Precision landing can be done. Fuel consumption can be done, and then the environmental friendly. So all those benefits, as we discussed, generic in the previous slide, same are available to us here also. So these are the locations. The yellow dot here depicts the location of the continuously operating reference station which we have established at Dehradun, and this shows the GSAT-10 location in the geostationary orbit. This one we have chosen. This is the Trimble pivot visualization software which we are using for this purpose, and this is the location of the GSAT-8. Now, similar to the VAS and GAGAN system, there is a IGNOS system which is available for Europe. Here again, same. They have a reference station on the ground, and with the use of the geostationary satellites in the orbit, they are sending the corrected signals to the users. Now, besides that, they are also using the internet-based transmission for the correction signals also, for the dissemination of differential correction and using the entry protocols. So that is also there, and there is an agency called Eurocontrol which is taking care of all these activities in the European region, which has 38 member states. Okay, so basically we can see that in case of Galileo also, large number of countries in the Europe are part, and in the IGNOS also it is same. Now in the case of IGNOS, the initial system which is prepared using the 40 ranging integrity monitoring stations, primarily it has been working on the principal feed from the GPS signals only. Similar to the GAGAN or the VAS, here also the dependencies on the GPS. However, as the Galileo is moving towards completion, they were planned for the IGNOS 2.0, where their systems will work on the GPS as well as Galileo. So that kind of system they will have, and they have 2 mission control centers, 6 navigation land earth stations, and they have a IGNOS wide area network. So this is the location of various stations what they have put across the European region. So we talked about the VAS of the US, then the GAGAN of India, and then the IGNOS for the Europe. Now this is the quasi-zenith satellite system of the Japan, and this is using the Michigi satellites, which means to guide. So they are also using it for the regional navigation satellite system also, as well as for the purpose of the satellite-based augmentation system also, using the Japan MTSat satellites. These MTSat satellites are providing the SPAS support using the DGPS methodology again, and they are supplementing the GPS system. See, again, GPS is providing 10 to 20 meter accuracy as a standalone, but with this MSAS system, what they are able to provide is 1.5 to 2 meter in the horizontal and vertical dimensions. That is the kind of improvement they are able to make. So they also are using the MTSat-2 satellite for this purpose in the geostationary orbit. So the MTSat-2 is in the geostationary orbit. These are the GPS satellites from where the users are getting the primary feed for the coordinates, and on the ground they have the again reference stations and then the uplink stations. So these are able to upload the corrected signals to the MTSat satellite, which further disseminate the signals over Japanese and neighboring region for the purpose of user. So you can see here a snapshot of one of the location there, and you can see there is a large number of availability of satellites like GPS, GLONASS, Galileo, ASPAS, QZSS, and VIDO. So large number of satellites are there. So this is again a depiction of that. So the master control stations are there, and Australia also they have master reference stations, so that some utility can be there in the Australian region also towards the south side of the Japan actually. Because this Japan, as you might have noted in case of the IIRS, which we will cover next week, that they have a formation of 8 actually, which appears like 8 actually when they are moving in the inclined orbits. A similar thing happens in case of the QZSS. So wherein it can provide some services to the Australian region also because of the availability of the footprint. So these are the photographs for the telemetry and tracking command stations in the Japan region. So again, we can have some kind of cues here. However, let us move further. So now for the China and Russia, that is remaining. So for the Russian region also, they have a system fully functioning for the SBAS based on the GPS and the GLONASS. Both are being utilized here, and the system is called System of Differential Correction and Monitoring. That is the SGCM. Here also in case of Russia, they are also using the GSM broadcast from SysNet server and the Encrypt server. So they have a facility from the SIM card based system also through the mobile services as well as through the internet services. So that kind of system they have for the Russian region, and they are on the move for the further improvements. Using this SGCM system, they are able to provide 1 to 1.5 meter accuracy in the horizontal plane and 2 to 3 meter of accuracy in the vertical height. So they also maintain the SGCM system like this. And in addition, they are attempting for providing the centimeter level positional service to the users within the range of 200 km from the reference stations. Okay, as we are moving from the reference stations, there is a deterioration in the accuracy. However, they are using the GNSS technology combined with the SBAS technology using the known reference stations, and they are attempting to provide centimeter level accuracy for the different users. These are the footprints of the geostationary satellites which are being used by Russia. So 5B, 5B and 5A, they are providing the SGCM service for a very large region. In this case, what I see, there is a VAS system for the US, and for the Canadian region, it is called the CVAS, Canadian VAS, the Canadian Wide Area Augmentation System. So for the China has already used the design which is very scalable. So in the BEDO one, they have developed the BEDO constellation for the functionality in the China. For BEDO 2, they have used it for the Asian region, and for the BEDO 3, which is the final BEDO actually, it is functional for the entire globe. So it is capable of providing the differential solutions also using the SBAS system. And this service is available in the Chinese region from December 2012, and they are using the GPS L1CA based signal and the BEDO geostationary satellites for it purpose. As I told, so these source of the screenshots are also shown here. All the details about the satellites involved, they are being displayed all the time on the respective websites, and they also do have some inter website linkages also. So from one government website, you can go to the other government website where they are taking care of the BEDO, GLONASS. So basically the European agency, Chinese agencies, they also have their links for various inter-constellation details. So that kind of information is also being shared. Now, satellite-based augmentation system is also there for the South and Central American and Caribbean region. and it is founded by participant member states, including the Argentina, Bolivia, Colombia, and so on. So like that, we can primarily see that almost all over the globe, the ASPAS systems are now available or are in process of preparation. So what we, for the inter-country or the intercontinental flights, what they have to do is that when they are moving from one region to another region, they should opt for a nearest S-bus system, because the nearer we are to the reference stations, the more accurate values we are going to get. So that was about the satellite-based augmentation systems, and then we have other stations in the GNSS category, like the continuously operating reference stations, which are highly useful for the tectonic studies. And these are spread all over the globe, maintained by different private, public, and academic organizations. Something like 2,000 GPS tracking stations are already there, which are provided by the 200 plus organizations. Now, some of the data sets are online available, or some can be obtained by registration process, as I have told you the previous lecture. So Survey of India also have now many course station function, and the government agencies can register there and they can get the course data. In that case, they will not need the establishment of the base station. They can directly do the survey through the rover stations. So this is the course station which is installed at IIRS. So the Department of Space has also established a lot of stations across India. Like a National Remote Sensing Center has established, SAC is involved from Ahmedabad, and IIRS from Dehradun. So we have also established various stations for the tectonic studies, wherein this data is very valuable because it's working 24 hours, 365 days. So it collects a lot of data. So any movement which is happening on the ground because of either tectonic movement or earthquakes, so all that data gets recorded, and this can be further analyzed. Then there is a GDGPS system is there, which is a high accuracy GPS augmentation system developed by NASA JPL to support the real-time positioning, timing, and determination for the NASA science missions. So now this do not require any independent local infrastructure. That is the advantage of this system, and this is capable of giving a sub-decimeter level of accuracy. So that is the kind of developments which has already taken place in this, and what is in future is the tracking and data relay satellite system based mechanism, which is called the TAS, that is the TDRSS augmentation service for satellites. And this service will have the responsibility to provide the position of the near Earth spacecrafts or the small satellites within an accuracy of 4 inches. That kind of system, that is TAS, is being under investigation, and it will work actually. It will also be working. So besides this, we have the IGS stations, International GNSS Service. So in the beginning, they were called International Geodesy Stations, and when the GPS was formulated in 1990s, when the IOC FOC completed in 1993-94, and the IGS stations started working there, so then it was renamed as International GPS Service, and once the concept of GNSS came in 2006, so it was renamed as International GNSS Service. So in this also we have now about 500 GPS monitoring stations under the IGS category all over the globe, which are again contributed from various organizations, and these IGS station datasets can be downloaded free of cost and can be utilized for the high-end processing actually. So these systems are fully available for the users. So because I checked some time back, so now the current number is the 506 So 506 IGS stations are already operational and data sets are available. So in case of India, we have the IISc Bangalore station is there, then NGRI Hyderabad, and third station is by ISRO in Lucknow. And then few more stations are about to come in India, like at Port Blair, Dehradun, Jodhpur. So these stations will also soon start providing the data sets once they are fully certified for the purpose of users from the respective agencies actually. So using these different kind of services, we have a lot of service providers now, like the Starfire is there, Starfix is available, and Starfix is committing for providing an accuracy of 10 centimeter in horizontal and 20 centimeter in vertical. So basically these services are paid services and you can have the license for these services. So similar services are there from the Omnistar. Then for the iPhone users, TomTom Telematics is there. So TomTom Telematics is providing the position as well as the image in the background. Very high, like very good resolution data sets are available, which are provided by the TomTom services when you are using it for the purpose of navigation, for your purpose of travel or any other application. Then Trimble is also providing the RTX satellite vehicle and RTX RX based on the internet. So through the internet as well as through the satellite, both services are available from the Trimble navigation. Similar service is available from Leica also, Mix Telematics. So these all companies are providing a lot of services for the users, which can provide high accuracy for the different application in real time. So primarily today's lecture basically intent for the users or the scientific community or the research community who have something to do with the real-time solutions. Because see, if we have interested in post-processing, we can do the survey and we can process later. But for applications like the aircraft industry, where we need real-time accuracies for landing, travel, en route, and the descending or the departure, all the stages of aircraft, for those applications, we need the SBAS systems. So if SBAS systems are there, our reliability is higher and accuracy is much higher. So thank you very much. This was the topic which we wanted to cover today under SBAS. So now it is to you. You can ask various questions. And the questions which you want to ask today can be from any of the 3 lectures which we have taken till now. The first lecture was on the basics of the GPS and the GNSS. Second was on the receivers processing, and today is on the SBAS. So you can ask questions related to all these. Thank you.